Peter, when you switch coordinate systems inside an integral, what do you multiply by?
I just swap the variables and call it a day. What else is there?
That's exactly how you fail a calculus exam. You mathematical delinquent. You need the Jacobian. Let's start simple. In single variable calculus, u substitution says du equals u prime of x times dx, so changing variables introduces a scaling factor. That derivative scales the width of each slice.
Right, because stretching the variable stretches the little slices you're adding up.
Exactly. In multiple dimensions, that scaling becomes a matrix. The Jacobian is the matrix of partial derivatives, and at each point it is the best linear approximation to your coordinate map. Look at this. On the left, a uniform grid in UV space. On the right, after mapping to XY space, the squares warp into curved patches. If you zoom in on one tiny square, Jacobian tells where its two edge directions get sent.
Whoa, some of those patches are way bigger than others.
Exactly. Those mapped edge vectors can rotate, shear, and stretch. So Jacobian is not just one scaling number, it is the full local transform. Here's how you compute it. Write the partial derivatives of x and y with respect to u and v. Column 1 is where a unit u direction step goes. Column 2 is where a unit v direction step goes.
So for a tiny move in uv, I multiply by j and get the corresponding tiny move in xy.
Correct. In symbols, the tiny xy displacement is approximately j times the tiny uv displacement. That is the core meaning of Jacobian. Now take the determinant. For any linear map in 2 dimensions, determinant is the signed area scaling factor, the area of the mapped unit square.
Why the determinant, though?
Because J maps a tiny square to a tiny parallelogram spanned by its 2 columns. That parallelogram's signed area is the determinant of J. A smooth nonlinear map is locally linear, so the local area factor is absolute value of the determinant of J.
So the sign says whether orientation flipped, and absolute value keeps the pure area stretch for integrals. That's clean.
Let's do the classic example, polar coordinates. X equals r cosine theta, y equals r sine theta. Build the Jacobian matrix from those 4 partials. When you take the determinant, the trig pieces collapse, so the whole factor simplifies to just r.
So the local area scale only depends on how far you are from the origin.
Exactly. Farther out, the same tiny d or d theta patch covers more xy area, which is why dx dy becomes rd or d theta. The general change of variables formula, the integral over the old region equals the integral over the new region times the absolute value of the Jacobian determinant.
So anytime I switch coordinates, I just build the matrix, take the determinant, and slap it in?
That's all there is to it. Jacobian matrix, determinant, absolute value, done. Works for smooth coordinate changes with Kunyao Jacobian in any number of dimensions. Follow for more.